For our next speaker, it's my honor to introduce Ashleigh Adams from UC Davis. She's going to tell us how to add a bit of color to our face rings.
Thanks for introducing me, Trevor. So I am going to be adding a bit of color to your face ring. And I felt like as summer starts to come about that we should bring some color to our lives after a dreary winter. So my name is Ashleigh Adams. This work was done in collaboration with Vic Reiner when I was an undergraduate at the University of Minnesota. We are going to begin by talking about reviewing Stanley-Reisner rings, talking about F vectors, H vectors, Hilbert series. Then we're going to talk about something called a colorful system of parameters and introduce a new version generalization of Hockster's formula. Then we're going to talk about universal system of parameters and how these colorful system of parameters and these universal system of parameters relate to each other. We're going to start with an example. We're going to have our simplicial complex be this guy right here. And he's basically a set of sets that are ordered under containment. And so we've got our vertices colored here in pink, our A, B, C, D. And then we have our edges, and we have one-dimensional face. And so this one is not colored in, so that is not going to be a face. We define a Stanley-Reisner ring, so we can encode this information in an algebraic structure by setting our polynomial ring to be over some field K with vertices A through E. And then our ideal here is going to be generated by the minimal non-faces of our ring. And so what that means is all of these minimal sets, minimal meaning there's no other set contained in it, that is a subset of our vertex set. So that's A, B, C, D, E, but are not contained in our simplicial complex. So for us, that's A all the way over here to D. There's no face, one single face connecting those. AE, BD, and BE. And then, of course, our ABC face is non-existent. And then so we quotient out by this ideal, and that creates our Stanley-Reisner ring. This is one example of something we call a face ring. And there are many kinds of face rings out there, and this one in particular is of interest to us today. The dimension of a face F in our simplicial complex is going to be that size of the face minus 1. So you have the size of the set minus 1. And moving forward, an F vector is a way of keeping track of how many faces we have of each dimension. So in F minus 1, we always have the empty set, so it's always going to be a 1. Our zero face, we have 5 of those because we have 5 vertices, and those are our vertices. F1 will be our edges because our one-dimensional faces are all of our edges. And F2 is just the single CDE face. Now there's something interesting called the H vector, which was referenced before. We define our H vector in this star here, but we get it through calculating something called a Hilbert series. And our Hilbert series of our ring is defined as such, where we sum over the dimensions of each of the graded pieces of our ring, because this polynomial ring is a graded polynomial ring. And so we can start by looking at just taking this F vector, and we set it to t over 1 minus t to the d, and we compute that, and we should get our H vector if our F vector is correct. And those are these coefficients here in the series. And for this ring, for this Hilbert series calculation, is going 1, 2, -1, -1 t to the 3. And so this 3 is always going to be the dimension of our simplicial complex plus 1. So if you don't get that in the base, then you might want to recheck your calculations. And we can also compute our Hilbert series in a different way. We can do that from looking at our finite minimal free resolution of our Stanley-Reisner ring. And so when we resolve over K delta, we always get one copy of S. And so we're looking at K delta as an S module. And if you remember, our S is over some field and it's our vertices. So we always get one of those because there's always going to be a copy of our empty set. And furthermore, we also always know the length of this resolution. Computing our Hilbert series calculation, we have it nicely color coded here, but in our 0th point, for t to the 0, we always get this one copy. So we always have 1 times t to the 0. And then here, we're able to take our 4, goes in the coefficients here, our 1 goes into the coefficients here, and then the dimension here by which we're adjusting are going to be these the exponents here on our t's. So by looking at this resolution, following the color coding, we can create our Hilbert series. We can calculate our Hilbert series, reducing it down, and then by some elimination here, we obtain our Hilbert series. And so these are how these kind of two things relate. We can go back and forth between the two. Now we've constructed our Hilbert series in two different ways. How do we actually construct our minimal free resolution of K delta? So we first can consider a vertex selected subcomplex. So what's a subcomplex? It's a subset of our simplicial complex, which still maintains the essence and properties of a simplicial complex. And this one in particular, this kind of subcomplex, is going to be defined by a vertex selected subcomplex. So we take a selection of our vertices, and every single face that is contained in that subset, that becomes our new vertex set, and we build our simplicial complex, those that exist in our larger simplicial complex, off of that. And so our example here is we have the vertices A, B, C, D, and I have kind of grayed out the part of the complex that is no longer part of our subcomplex. And so off of this, we get A, B, C, and then we get this single vertex D. And so Hockster tells us that we're able to predict the shape of our complex by computing the dimensions of the homology of these subcomplexes, these vertex selected subcomplexes. Oops. So back to our resolution. Now notice that if we take, so let's just do one of these, for example, and if you're bored, you can compute the rest of them. But if we take the vertices AD, then this subset creates these two solitary disconnected vertices, and that gives us one copy of K. Similarly, another set of 2, BD creates another set of 2, and BE gives us another set of 2. And so what that gives us is 4 copies of K, and we're adjusting by 2, which is actually the number of vertices in these sets. So by computing these, by looking at the homology of these vertex selected subcomplexes, we're actually able to construct our resolutions. All right, are there any questions? Feel free to interrupt me at any time. Now, what if we consider a subcomplex that's defined slightly differently than our traditional subcomplex, our vertex selected subcomplex? All right. Now we're going to start by looking at giving our simplicial complex a proper decoloring. And so for us, we're going to give it specifically, we're going to try to color it with our number of colors being the dimension of our simplicial complex plus 1. And so by proper, what I mean is there are no two colors, there are no two vertices whose face contained in the same face who have the same color. So for us, that our coloring gives us blue and blue. We've got a pink and a yellow here in the center, so that no two colors, no two edges, no two vertices who are connected by an edge have the same color, nor do any that sit in a two-face. Now, if we look at the subcomplexes that are generated by these colors, what we get are, we generate by blue, we get these AE disconnected. If we look at the subcomplex by blue and pink, we get 4 disconnected vertices. So now from here, we are going to define our colorful system of parameters. Now you can always, for any kind of coloring, you can compute these polynomials, however, or these elements, but they aren't always going to be system of parameters. They're only systems of parameters when the complex itself is properly colored with the dimension of the simplicial complex -1 many colors. And so what we're doing is we're summing over each color. So our θ1 is going to be the sum of the blue colors. θ2 is going to be the colors of our 2 colors, and θ3 is going to be our 3 colors. Now we know that these are contained in our ring, and we've shown that they are a system of parameters when it's a proper coloring. And so what's nice is if we take a polynomial ring A and variable z through the number of colors, and we send zi to theta I to zi, and we're gonna have the action of zi acting on our ring by multiplication by theta I, then that gives us a k delta generated as a module. And not only that, but it's finitely generated, which means we can resolve over this A module. And what does this give us? A much, much shorter resolution than we had before. Much more simple to compute. If you remember, going back to our other resolution, it's pretty long. This one is nice and short. And if we do the Hilbert series computation, we get, I am missing a T. We get the we get our Hilbert series, which means these resolutions are both correct, and both resolutions for our k delta. Punchline, we can produce shorter free resolutions. Now, this is a theorem that Vic and I proved. It's a generalization of that previous Hockster's formula, and we call this the colorful Hockster formula. Now, when your coloring of your simplicial complex is trivial, so that every single vertex has its own color, then that just gives you the normal Hockster's formula with nothing special to it. But if you do give it this proper coloring, then we are able to predict the shape of our resolution by simply computing the homology of these color selected subcomplexes, giving us these much shorter resolutions, which are nice in very large, when dealing with very large and complicated simplicial complexes. But now switching gears a little bit, what if we consider an even more canonical system of parameters than these colorful ones? We call these the universal system of parameters. And that's going to be a sequence, θ1 through θd, where d is the dimension of our simplicial complex +1, where we simply sum over, each theta I is going to be summed over the I dimensional faces. So, or I+1 dimensional faces. So our θ1 is just going to be the sum over the vertices, θ2 the sum over our edges, and θ3 the sum over our 2-dimensional faces. Sorry, yes. And one very nice thing about these universal system of parameters is they're invariant under symmetries. Now, we did not dub them universal system of parameters, and they've been found in many, many works previously, first and foremost by Daconcini, Eisenbud, and Procasi, and they used them in algebras with straightening laws, Garcia and Stanton, in invariant theory of permutation groups, and D.E. Smith in sheaves of posets, and most recently, Herzog and Marty. And they, Herzog and Marty were the people who dubbed them universal. Now, another nice thing about these universal system of parameters is they actually tell us the depth of our ring. And that's going to be the max delta such that these thetas form a regular sequence. And that was a theorem that Vic and I proved this past winter. Now, we later found out that D.E. Smith actually had previously proven this for any pure simplicial complex. We generalized it even further than a simplicial complex, but for actual regular cell complexes that are related to a simplicial poset.
Ashleigh, I'm sorry to interrupt, but you're getting close to time here.
Oh, shoot. Okay. All right. Great. So the punchline is proposition that we can write both of these as K delta as resolution over our over the polynomial ring because it's finitely generated. Similarly, when we have these EIs acting on K delta as theta i's. So moving forward quickly is that we can relate these universal system of parameters and our colorful system of parameters by taking the barycentric subdivision of a simplicial complex. Now that's still a simplicial complex, so it still has a Stanley-Reisner ring. And moreover, our universal system of parameters for a simplicial complex are conjecturally the same as the system of as the colorful system of parameters for the barycentric subdivision. And so sending these each to our ZIs and acting on the respective rings of the simplicial complex and the barycentric simplicial complex, we conjecturally get the same shape of our resolution. And by that, if we do know that, if this is true, then we actually know the shape of the resolution because of the colorful Hockster formula, which gives us our resolution for the barycentric subdivision. Evidence, there's quite a bit of it. We have an upper bound on our dimensions, but we can't seem to figure out how to prove it. We believe the right way to prove it is actually by going about a question, which is not quite a conjecture yet, but we actually believe that these rings are going to be exactly the same when generated as A modules. Our evidence is we haven't found a counterexample. So, and one more note is that everything we've done on a simplicial complex today has actually been generalized to simplicial posets and a corresponding face ring. Yes. And right, in this case, our simplicial poset, the barycentric subdivision, is a simplicial complex. And so this colorful system of parameters is in fact a system of parameters. So thank you very much. The paper is on the archive. I'm going to upload these slides if you have any more questions. And there's also a Macaulay 2 package that I created for this project that exists on Macaulay 2 if you want to play around with any of these things. Thank you very much.
Thanks so much, Ashleigh. Great talk. Invite everybody to thank Ashleigh for her talk. Are there any questions?
I have one. I'm wondering, like, is there a philosophical reason why the resolution for the A module is so much shorter in general?
Yeah, so I guess the way you can think about it is these system of parameters are invariant under symmetries. And so we've cut out everything that isn't really necessary. And so we're just going down to these invariant parts, which gives us this like cleaner resolution.
Thank you.
Are there any other questions? If there's no other questions, let's thank Ashleigh again.